In honor of Pride Month, I'm using the pink chalk. How's that? Sai, how's this? Sai, does this work?
Yeah, with my phone.
You can start.
Get going. Bob is industrially his board. Is speaker, at least I know. Robert Lubarsky from originally to speak about the reverse mathematics of
Oh.
take it. The title is now Harrington's principle.
Thanks, Russ.
Go right ahead.
So I had prepared slides for the talk, but I determined yesterday that they did not really capture my thinking about things at the moment. So a chalkboard talk. Of course, the challenge with giving a chalk talk is that you have to remember what you want to say. Wish me luck. So, the interest of Harrington's principle, if any, is that it's well known that there is an equivalence between zero sharp, the existence of zero sharp, and pi1,1 determinacy. But all known proofs of the one direction go through Harrington's principle. So that's why this is of interest. And you can then, well, in one direction of that equivalence is that Harrington's principle implies the existence of zero sharp. So one could well ask the question, if you look carefully at the proof, you don't really need all of ZF for this. In fact, and this is understood as folklore, fourth order arithmetic. So what do you really need to get this proof to go through? The proof, if you look at it closely, needs aleph 1 and aleph 2. And that's where the fourth order arithmetic comes in. Because if you think of so what's second order arithmetic? Well, if you're in L aleph 1 is quite enough to get you second order arithmetic. You don't even need this much, but you need something that looks like L aleph 1. So you don't even have aleph 1 as a set in second order arithmetic. In third order arithmetic, you basically have one iteration of the power set. So now you get aleph 1 as a set. For third order arithmetic, it's quite enough to be in L aleph 2. So you have aleph 1 as a set, but not aleph 2. In order to go through this proof, you need aleph 2, so that's going to be fourth order arithmetic. So if you're in L aleph 3, you have a model of fourth order arithmetic, you have those two cardinals, all is good. So over fourth order arithmetic, this implication goes through. You could well ask, what's the consistency strength of Harrington's principle over a weaker theory? And it doesn't take a lot of thought to realize that if the base theory is weak enough, Harrington's principle doesn't get you anything. So for example, if you're working over, let me just say, ACA, Harrington's principle gets you nothing. Because, ACA, the simplest model of ACA is all the arithmetically definable sets. So you're working over L omega, basically look at L omega plus 1. That's a model of ACA. And Harrington's principle, that's just true. You know, every admissible ordinal, well, there are no admissible ordinals. Or if you will, omega is an admissible ordinal, and omega is a cardinal in L. Harrington's principle is just true there, so it doesn't get you any consistency strength. So natural questions are, if you're working over, let's say, Z2 or Z3, what consistency strength does Harrington's principle get you? Well, there was some work done along these lines. The basic theorems were shown in a paper by Chang and Schindler. And they figured out that over Z3, Harrington's principle is equiconsistent with the remarkable cardinal, which it's a large cardinal property. It's less than 0 sharp. It's kind of complicated to state and just a bit off the main thread of this talk. So if you're interested in that, I'll refer you to the paper. Another theorem that they showed is they got the equiconsistency result between second order arithmetic and Harrington's principle with ZFC. So, okay, I mean, ZFC, it goes beyond Z2, but it's a lot less than 0 sharp. So what what Juan and I started to look at was a refinement of this. That is, if you think about the natural subsystems of second order arithmetic, basically pi 1n comprehension, the question was, what fragment of ZFC does that correspond to? So let me try to make this sound more difficult than it actually is, just so you feel as though you got your money's worth by coming over here. The connection is not immediately clear, because if you think of subsystems of Z2, so you think pi 1n comprehension. Okay, so this is a comprehension axiom. If you think about subsystems of ZF, most of the axioms are single axioms. If you're going to stratify ZF, I don't know about you, but the first thing that comes to my mind is replacement. You could think about, let's say, sigma n replacement. And so over there, and it's not immediately clear how you're going to connect these things, because this is a comprehension axiom, and replacement doesn't always naturally line up with comprehension. If you think, for instance, of L aleph omega, you get full comprehension here, but only sigma 1 replacement. You don't get much replacement at all. So it's not clear how to connect those two theories here. But fortunately, we are in a somewhat different setting. We can do better than this. So a little bit of fine structure here in order to help us make this connection. And I'm going to attribute this to Jensen. That is my impression, that the little bit I'm going to say is attributable to Jensen. If I'm making a mistake, I hope somebody will correct me here. That if L alpha has a largest cardinal, so that's what takes care of counterexamples that look like this, then I'll phrase it first in terms of admissibility here. L alpha is admissible if and only if L alpha satisfies delta 1 separation. That's what it's called in set theory. It's comprehension in arithmetic. This alone does not suffice for KP. But if you're an initial segment in L with a largest cardinal, then it's a way of understanding admissibility, how much separation you have. And you can even bump this up a bit. More generally, L alpha satisfies sigma n admissibility. I believe Antonio described what this was. Basically, KP has a certain amount, it's like delta 1 separation and sigma 1 replacement. Well, this would be sigma n, delta n separation and sigma n replacement. So that's for initial segments of L with the largest cardinal. This holds if and only if L alpha satisfies delta n separation. Okay, so that helps, but we're still going to have to take a couple more steps. Let me at this point make the translation from arithmetic to set theory. One of the things that you need to pay some attention to in order to get this equiconsistency result is to realize that we're talking about two different languages over here. On the one hand, we have the language of arithmetic, and then over here we have the language of set theory. So there's, should I call this bi-interpretability, or let me say translation. Yeah, let me use that word instead. Translating between arithmetic and set theory. I don't know how standard this is. This is all in Simpson's book. You can see Simpson for this. But during the break earlier, Cy was leaning on me about this. So that gives me the confidence that this is at least worth mentioning. You can translate between theories of the two. So if you have any kind of set theory, you can interpret the arithmetic in set theory. Well, set theory is enough. You have the natural numbers and sets of natural numbers. So it's a sub-theory. And you could, if you have some axioms for set theory, by referring to reals, whatever reals you happen to have, you get a theory of arithmetic. So set theory contains a certain amount of arithmetic as a sub-theory. So this is how you can interpret arithmetic within set theory. In the other direction, you can interpret set theory in arithmetic by looking at well-founded trees. You can take a well-founded tree given by a real as representing a set. If you have a well-founded tree, you can think about the Mistovsky collapse of the tree, and that gives you a set. So you can code sets that way. Arithmetic interprets set theory using well-founded trees. So this ends up being very nice when you're dealing with strong enough theories of arithmetic. So Pi1n comprehension is mutually interpretable with on the set theory side, KP without foundation, with set foundation only, plus pi n minus 1 separation. So this would be a good moment to mention over here that for this to work, n has to be at least 2. When n is 1, this doesn't quite work well. You need a certain amount of set theoretic power for this to happen. Plus, every set is hereditarily countable. Okay, so if you're looking at subsystems of Z2 with Harrington's principle, we can use this to translate it to set theory. So what would be the natural set theory that would go along with this? So this is pi n minus 1 separation. That doesn't fit in quite yet with admissibility. A certain higher level of admissibility is equivalent with delta n separation. How are we going to get something like pi n separation? Well, this is non-projectability. So we have that L alpha is sigma n non-projectable if there is no one-to-one sigma n over L alpha, sigma n definable function from L alpha into a set in L alpha. So, for instance, L omega 1 ck is sigma 1 projectable. There is no sigma 1 bijection between L omega 1 ck and a set. That would violate admissibility, but you can get an injection into a sigma 1 definable subclass, a subclass here being a subset of omega, is sigma 1 projectable into omega, no less. So sigma 1 non-projectability in the presence of a largest cardinal is a stronger property than sigma 1 admissibility. So I think in the presence of a largest cardinal, you have sigma 1 admissibility is a weaker property than sigma 1 non-projectability, which is weaker than sigma 2 admissibility, which is itself weaker than sigma 2 non-projectability, and so on down the line. And it's the non-projectability that's going to be of interest to us. So the fine structural result here is that if L alpha, again, in the presence of a largest cardinal, has a largest cardinal, then L alpha is sigma n non-projectable if and only if L alpha satisfies sigma n or pi n. Did I write? Yeah, I wrote pi n before. Pi n separation. Okay, so this is what's going to get us the exact connection with a subsystem of arithmetic. What's the nicest way to phrase this in terms of set theory? Well, again, in the presence of a largest cardinal, another equivalent formulation is that L alpha is a union of a chain of sigma n elementary substructures. Okay. So this comes down to reflection, which I think of as another clean way of understanding the axioms of ZF as a hierarchy. So when you're doing, in my intro set theory course, one of the things that I learned was, well, like one of the big axioms of ZF was replacement. And replacement over the other axioms of ZF was equivalent with collection, which ultimately is equivalent with reflection. Now, in the presence of some sort of weaker context, these things are no longer equivalent necessarily. If you don't have power set, for instance, or if you don't have classical logic, if you only have intuitionistic logic, then some of these equivalences can break down. So you have soft proofs that reflection implies collection, which implies replacement. The other directions need some work. Over the other axioms of ZF, you got it, or maybe even ZFC. No, I don't think you need choice along the way. But it's using reflection over here. That's what can give you this nice stratification of ZF. So I will take ZF to be here. Some of the basic axioms, pair, union, things like this, plus delta zero separation. You end up needing to assume a little bit of separation, plus the schema of sigma n. Let me call this ZF ref, so you don't confuse it with using replacement or something for the axiom. The schema of sigma n reflection. And then I will take ZF nref is what happens if you restrict the reflection schema to just sigma n reflection. Is just ZF ref with only sigma n reflection. And so the theorem that I can finally state, and this is for Han and me, that you get the consistency of pi 1n comprehension with Harrington's principle, the equiconsistency of that with reflection over ZF restricted to sigma n formulas. Okay, so it took only half the talk or something, even more, to get to the statement of the theorem. Yes? Over all n. Yes, yes, that's what makes it a schema. So if you fix n, you can write that as a single axiom. Okay, this is a natural moment to pause. Any other questions? Okay. Thank you. Yeah. So the idea behind reflection, you could pick any, it's supposed to be that if you have a sigma n formula, let's say in one free variable, this would say that there is a transitive set X which reflects the truth of this sigma 1 formula And so for every sigma n formula, there's a transitive set A, not to confuse it with X, which correctly evaluates that formula, such that for all B in A, B holds on B if and only if in A, phi holds on B. This is sort of the most abstract way to present it. Now, the way I like to think about it is you can take a universal sigma n formula, and without loss of generality, you can get from this that A has to be an initial segment of V. So equivalently, I should say for every formula and for every Z, there's a transitive set containing Z. So there are unboundedly many such things. So a nicer formulation of this ultimately is that for every alpha, there is a larger, I'll call it beta, there is a larger beta such that V beta is a sigma n elementary substructure of V. When you clean it up and get to the heart of the matter, that's what sigma n reflection comes down to, that there are unboundedly many initial segments of the V hierarchy that are sigma n elementary substructures of V. Is that good? Since I'm only talking about consistency, then I can work in L, and then it's the same thing. But you have a good point. You realize that if n is big enough, I think 2 is enough, certainly 3, that in order to be like a sigma 2 or sigma 3 elementary substructure of V, you have to be an initial segment of V. You just look at statements like the power set holds, and that the power set is computed correctly. To say X is the power set of Y is a pi 1 statement. So once n is big enough, you have no choice. In order for this to hold, it has to be an initial segment of V. For n equal 1, you can get away with a set that's not V. You can get sigma 1 elementary substructures that are not an initial segment of the V hierarchy. But you don't have to. You can get by with just restricting. Yeah. Yes.
The problem is you might not have a lot of. You could just say for every X.
Well, what Juan is pointing out is that when n is 1, there is other stuff going on. That already came up over here.
This applies to the rest of the part.
Yeah, well,
Okay.
no, I need to deal with the case when n equals 1. It's just that somebody once said that your intelligence is inversely proportional to your distance from the chalkboard. I am not in a state now to be able to evaluate what's happening when n equals 1. I cannot do so. Please don't ask me to. You can think n is bigger than 1, and you'll be mostly good. So maybe with the little time that I have left, I can say something about the proof of this. So let's see, thinking about n equals 2, because it is a separate case. So so the easier direction is that if we start with pi and comprehension, along with Harrington's principle, I want to get sigma and reflection. So how is this, pi 1 and comprehension? So why do you get power set? Because sigma, that's like the big axiom, but the other big axiom in ZF, which we still have, is power set. So where does power set come from? Well, that comes from HP. So the hyperjump when you have, just think about, oh, the hyperjump is pi 1, 1 definable. So if you have pi 1, 1 comprehension, which you certainly do, then the model that you're starting with here, you can prove that whatever you have is closed under hyperjump. So this theory proves, you don't need HP for this, that for all x, the hyperjump of x exists. A hyperjump is just what you need to get the next admissible set. So the real that HP gives, so remember HP says we're working, you pick a real G where all the admissibles are L cardinals. Well, pi 1, 1 comprehension is enough to get unboundedly many admissibles. By Harrington's principle, you now have unboundedly many cardinals in L. So just stick in L. By HP, we have unboundedly many L cardinals, which, if you know some fine structure, that's enough to get you the power set in L. Okay, that's a nice start. Now, how are you going to get reflection? Well, with pi 1 n minus 1 comprehension, you have pi 1 n comprehension. You get pi n minus 1 separation. Notice you lost a quantifier here. So this is enough to give sigma n minus 1 non-projectability, which is enough to give you sigma n minus 1 reflection. But we need sigma n reflection. So let me jot at least this much down. Pi 1 n comprehension gives pi n minus 1 separation, which is sigma n non-projectability, sigma n minus 1 non-projectability, which is sigma n minus 1 reflection. How do we get the additional quantifier back again? Well, here we are working relative to the real given by Harrington's principle. So we get pi n minus 1 separation in L of G. G is for Harrington's principle, and that carries through all along the way. And then if you go to L, that's where you get the extra quantifier, because all of the admissibles that we have here are cardinals in L. And you can go from each, in L, if you have cardinals, you get sigma 1 elementarity. So if you want to evaluate something sigma 1, in L you can go up to the next cardinal, but if we have G at hand, you just go up to the next admissible. And that's delta 1 definable. For every admissible larger than kappa, or for some admissible, or for any admissible, G admissible larger than kappa, you go to evaluate in anything which is, sigma 1 true is going to show up by the next admissible. And so that's how you get an additional quantifier. Way on the inside, that existential quantifier right on the inside can become delta 1. So you get sigma 1 reflection in L. So that's kind of the easy direction. In the other direction, if you start with sigma n reflection and you want to get, well, to get pi 1n comprehension, this you're going to get for free. It's a matter of getting Harrington's principle. Now, it may not be true over here, it's just consistency, okay? If this is what you have, then for all you know, you're in L. Certain initial segments of L and satisfy sigma n reflection. So we're not getting that Harrington's principle is true, we're getting the consistency over here. And how do you do that? Well, by forcing. So you need to force to get a real with the right admissibility spectrum. So the admissibility spectrum of a real is the set of ordinals that are admissible relative to that real. And if you take as your admissibility spectrum the cardinals in L or any nice subcollection of those cardinals, then the task becomes to force a real with that admissibility spectrum. This then picks up an old result of Jensen, which becomes critical when doing this. So what Jensen showed is that if, I'm going to need a little more room for this. Shouldn't have erased Jensen's name. I had already. Could have saved myself that much work. So, Jensen, if A is a countable sequence of countable ordinals that are admissible relative to the sequence itself. If you have a real, then its admissibility spectrum is easily definable from that real itself. So if a countable sequence of countable A admissibles, then A is the beginning of the admissibility spectrum of some real. So, Jensen's argument for this is a forcing construction, but the conclusion is not a consistency thing because you're working over a countable set. The countable set of countable admissibles, your bottom universe, so you start over L of the supremum of A. And then you do a forcing construction, but you can get a generic in V because there are only countably many dense sets that you need to hit. And so that's why in his setting, he gets a real existing in V. Our setting is a bit different. We actually have to force to get the real in question. Now, Jensen's result doesn't apply directly over here because the way Jensen kills the first step in Jensen's argument is you don't want to destroy admissibility, sigma 1 admissibility, but you end up needing to destroy any stronger property, like sigma 1 non-projectability or sigma 2 admissibility or anything like that. We need to preserve that. We need to get reflection in the end, so we're going to need to preserve a certain amount of non-projectability. So the argument has to be somewhat different. For the case n greater than 2, for the case n equals 1, then you really need Jensen's techniques. And there's certainly, I had no intention of going into the details of Jensen's construction because it's very intricate and there's a lot going on there. And it was probably a bit too aggressive of me to try to give any proof at all here. I'm certainly not going to go for this. And I think that I've pretty much used up my time and gotten to say the essence of what I wanted to say. Thank you for your attention.